Black holes are, in many ways, the most extreme objects in the universe. They pack an enormous amount of mass into a smaller volume of space, bending the fabric of spacetime so much that once something enters a certain region, it can never escape, even if it is moving at the ultimate cosmic speed, the speed of light. It appears that trillions of black holes, some of them reaching billions of solar masses, are distributed throughout each galaxy in the universe, including our own Milky Way. And yet, if we consider how all these black holes were formed, we can confidently say that each one was initially made of ordinary matter. None of them were formed from dark matter, even though dark matter outweighs ordinary matter by a ratio of 5-to-1 in the universe. But if black holes are the result of gravitational force and dark matter reacts to it, what then prevents the formation of a black hole from dark matter? Today, our cosmic story is about whether black holes can be made of dark matter, and if not, why not? In our modern universe, only a few ways of forming black holes are known. Perhaps the most common method is the collapse of the core of an extremely massive star. The only thing that holds stars back from gravitational collapse is the energy produced by nuclear fusion in their cores, where external radiation pressure balances internal gravitational force. When the fuel that a star burns runs out, the pressure from radiation begins to drop, and the star's core begins to compress under the influence of its own gravity. As the core compresses, it heats up to a temperature that is difficult for the average person to imagine, and the higher the temperature, the more likely the core is to start burning even heavier elements as fuel. And after these elements are exhausted, the core collapses, resulting in a Type II supernova. If it is massive enough, a black hole will form due to the accumulation of enormous mass in such a tiny volume of space. If the core is not massive enough, a neutron star is born instead. In addition, a black hole can also form as a result of the collision of two neutron stars, provided that the total mass after the merger exceeds a certain threshold. Finally, a black hole can form as a result of direct collapse, when, for example, a single massive star simply becomes too dense for light to escape from a certain volume of space. As soon as this condition is met, an event horizon is formed, and everything that crosses it is guaranteed not only to never escape, but also to quickly increase in mass, and therefore the size of the black hole being formed. In a short amount of time, it can swallow up all the mass of any object from which it was formed, and then a black hole will also appear. Other exotic ways of forming black holes can exist, but it is believed that the aforementioned ones are responsible for the overwhelming majority of existing black holes in the observable universe. As you may have noticed, all of these methods have something in common. They are based on ordinary matter consisting of atoms and their components. This becomes even more amazing when you consider a number of facts. Ordinary matter makes up only 1/6 of the total mass of the universe, while dark matter makes up the remaining 5/6. Both normal and dark matter experience gravitational force equally, obeying the laws of Newton's and Einstein's gravitation in any medium where there is an abundance of normal matter. For example, in a galaxy similar to the Milky Way, there is generally much more dark matter with a ratio of at least 5-to-1. But then why can ordinary matter so effectively form black holes, while dark matter cannot? The key lies not in the force of gravity, but in other forces such as friction and collisions that depend on electromagnetic interaction. Ordinary matter experiences this force, but dark matter does not. When a galaxy forms, dark and ordinary matter typically form in a ratio of 5-to-1, on average, as does all matter under the influence of gravity. Both types of matter are attracted to the center of the gravitational potential and accelerate in that direction. The interesting part starts when dark matter penetrates through the galaxy. It does not experience frictional heating, interact with electromagnetic radiation, or have the ability to exchange energy or momentum with other existing particles inside the galaxy. It will remain on a slow orbit with a large angular momentum, and it may take about 1 billion years to form a complete ellipse. Ordinary matter, on the other hand, has everything that dark matter lacks. It collides with other particles of baryonic matter, which can exchange energy and momentum, and particles can collide, leading to losses of kinetic energy and angular momentum. It experiences friction and heats up when interacting with other particles of ordinary matter, responding to radiation. All of these phenomena lead to a significant difference that can be summarized as follows. Ordinary matter loses momentum and angular momentum and sinks to the core of the galaxy, while dark matter always remains diffusely distributed in a vast space, creating. Other particles of the baronial substance can exchange energy and momentum and collide, which leads to a loss of kinetic energy and angular momentum. They experience friction and heat up when interacting with other particles of ordinary matter, responding to radiation. In combination, all these phenomena lead to a significant difference that can be summarized as follows. Ordinary matter loses momentum and angular momentum and falls into the core of the galaxy, while dark matter always remains diffusely distributed in a huge space, creating a halo around the galaxy. Ordinary matter forms separate dense small clusters, while dark matter forms rare clusters, but mainly of very large size, without a mechanism by which it can transfer angular momentum. Dark matter can never even approach the density necessary to create an event horizon, and therefore there are no black holes made of dark matter. Hence, dark matter cannot collapse into a nucleus. There are no regions that have ever gathered enough dark matter to attract light back to themselves, which means there can be no dark matter undergoing direct collapse, and there are no stellar remnants or other relatively dense objects made of dark matter. Therefore, there is no way for rich dark matter objects to collide and form a black hole. All the mechanisms by which normal matter can collapse into a black hole do not work when applied to dark matter. Now it becomes clear that when a black hole is formed from ordinary matter, dark matter particles cannot cross the event horizon and increase the mass of the existing black hole. In this respect, dark matter does not differ from any other form of matter or radiation. When crossing the event horizon, everything inevitably falls into the central singularity and ultimately increases the total mass of the black hole. However, due to the clumpy nature of ordinary matter and the diffuse nature of dark matter, there are no realistic scenarios in which even 1% of the total mass of a black hole could be obtained from dark matter. Based on our current understanding of the universe, there is only one possibility for ever creating a black hole from dark matter, and that is if the very early universe had fluctuations of sufficient size that would quickly collapse and form a black hole long before the formation of any stars. If this had occurred, it could have created one or several primary black holes that existed independently of stars. In this case, only the mass matters because the calculation is based solely on the physics of gravity and the way structures form in an expanding universe. It allows us to determine how much excess density is needed to form a primary black hole that is independent of the average density. If the universe is born with an area that is locally 68% larger than the given average density, it will lead to a gravitational collapse and the formation of a primary black hole. Now we have a universe that was born with a spectrum of fluctuations, and these fluctuations have given rise to structures that we see everywhere in the universe. We see the consequences of these fluctuations in temperature defects in the cosmic microwave background, the signature of the cosmic microwave background in features such as correlation functions, and the power spectrum of large-scale structures in the universe. When it comes to scientific conclusions, it is important to ask the right questions and not give in to the temptation to mistake the desired for the real instead of asking whether it is possible to imagine. Scenario that bypasses current restrictions, which in the best-case scenario may give an option. Can I trust that it may be true? We need to look at the evidence and ask with minimal additional assumptions what the universe tells us about itself. Why can we conclude that it's true? And this key question of what is true lies at the heart of all science. Without evidence to support the truth of a hypothesis, it's irresponsible to conclude that the hypothesis itself is true from a scientific standpoint. When it comes to dark matter, as we understand it, we can expect that there are no black holes today or ever that are primarily or exclusively made of dark matter. There are no stars, supernova remnants, or scenarios of direct collapse that should have led to a black hole made of this matter, and there's no way for this matter to be dense enough to form a black hole after the universe began its existence. Unless we turn to a new but unobserved physics to cause the creation of a specific spectrum of primary black holes made of dark matter, we can say with confidence that ordinary matter is responsible for the black holes we observe today in our beloved universe. Don't forget to give this video a thumbs up, subscribe to the channel if you're not already with us, and until our next interesting encounter.